Okay, I'm going to say everything that I was just saying again. And yeah, basically, we're going to pick up where we left off. And I believe we were right on the edge of a breakout where we're comparing the outcomes from binary sampling dictionary for different numbers of samples. That's going to be this breakout. You're going to need a little bit of code for this. So let me get you that. You can also find this in the binomial.py file on the GitHub repo. But this, I'll paste this in the Slack for convenience. And one sec. You'll also need choice, right? So from random import choice is another part of this that you'll need. Okay. Okay, I think that's all you'll need, and let's just make sure. Yep. And yeah, last time, let's just look at this one more time. We did one trial of 1,000 samples, and I just want to reiterate kind of our findings when we run this. Let's do Python binomial. So if we're looking at this, we can see that these are counts, right? These are different counts of the occurrences of sums of bits, right? So if our 8-bit binary summed to 4, then we incremented the counter here, right? This 290. And as would be expected in a binomial distribution with probability 0.5, what we're seeing here is that 0.5 times n, n being the number of trials, 0.5 times n is the modal value, or what we would think of in the theoretical distribution is the expectation or the mean, right? So we've got 290, and then we've got kind of a relative symmetry about this. We don't have perfect symmetry, of course, because this is just, this is just one trial of 1,000 samples. So let's consider this breakout. I'll paste this code into the Slack. And this is more just describing, I just want a very brief description of the difference in outcomes between the two dictionaries, D1 and D2. So both of these should output, unless there's some error, which I'm sure you'll discover very quickly if there is. So go ahead and run this, and I'm going to put 3 minutes on, 3 minutes on the clock, and just describe what you see as different between D1 and D2 in terms of the outcomes, and how would you explain that? So let's run this. And maybe I'll put another 2 minutes on the clock. Sounds like there's a, well, yep, that is missing the values call, right? That's my bad. But, you know, let's call that a good opportunity for troubleshooting, maybe. That's a way that I can shift blame off of myself. Okay, so I'll fix that. And we're just going to take a look at these, and I'll, let's see. This is 16 bits, 100 samples, 1,000 samples, and what I'll do is snag these and kind of blow them up. So this is with 100 samples and 1,000 samples. Let's just make sure that that is correct. D2, D2 values, D1 values, D1, yep. Okay. So I'm going to put these side by side. And just take a couple minutes and describe what you see. Like, how do you explain the differences between these? Or, yeah, in your own words, how would you explain the differences between this this one that has 100 samples, right? So this is 100 samples. And this other one is 1,000. With more samples, there's more to the distribution. Yeah, for sure. And so, you know, when we have 100 samples here, you know, what we're going to see is, of course, this is going to add up to, you know, reasonably, you know, 1, all these probabilities. And what we would expect is sort of a clarity around what is and is more or what is less common. Really quick, if you scroll up, there's a chunk of code that I pasted in. Starts with from random import choice and goes down to def binary sampling dictionary. You're going to need that as well as the code that I pasted in for the challenge. So to run the block of code that I ran here, you'll need the code that I pasted in prior as well. Okay, so 100 samples is going to do 2 decimals, and 1,000 samples are going to 3 decimals. Does that mean more accuracy with more samples? Yeah, this is kind of the question. What do we gain here by having more samples? I think a way that I want to talk about this is in terms of error and uncertainty. And I'm going to move these aside for a moment. And we can kind of think about these two concepts, error and uncertainty. So what I mean by error in this case, you know, given that we would expect there to be symmetry in you know, in a perfect binomial distribution, in a theoretical binomial distribution, we're seeing somewhat of a lack of symmetry in this 100 samples, right? Like if it's 16, if we have an n of 16, if we have 16 trials and a 0.5 probability per trial, what we're going to expect is that our modal value, our mean here, is going to be 8, right? But notice 6 occurs a lot more in this one trial of 100 samples, and that is going to be you know, lead to something that's less representative. So we can think of 100 samples as being less representative of our true distribution. And we can see that sort of sampling error. If our goal is to approximately gather the parameters of the theoretical distribution, the theoretical binomial distribution here, we're kind of not doing a great job with this 100 samples, and that's due to not having enough samples. Now, we're going to do better over here, right? Where we do have, clearly we have 8 as our most common value. And we do have kind of an emergent symmetry around that. And it does pretty well, right? Like 4 and 12 should be symmetrical, but, and they are. They're, according to our calculation here, they totally are. Now, what we can do a few things to do better than this one, than our 100 samples. There's a couple things that we could do. The obvious one is take more samples, right? That's going to, if we had 10,000 samples, these numbers would start clearing up, and they'd look a little bit better. The other thing that we can do is we can do many trials of 100 samples, or many trials of 1,000 samples, and that's going to lead us to something that looks much, much more like the actual theoretical distribution that we saw with counting. Something else you might notice here is we never capture 16, and we never capture 2, 1, or 0 here. And then we also don't capture 14. Notice that? We don't capture 14. So this occurrence of 15, that only occurred one time. And yeah, that's just what we're seeing here. And, in this case, we don't have any gaps, right? We don't have any gaps in this 1,000 samples, but we also don't capture 14, 15, or 16. We don't capture 0 or 1. So we can see right there that if we took more samples, it would be more probable that there would be an occurrence of 16 ones or 0 ones, right? But we would need to take more samples. Or we would need to take more trials of samples. I'm going to argue for this trials of samples approach, and we'll see why in a second. If I was to run multiple trials with smaller samples, I would average those trials exactly. I would average them, yeah. And so we can build something that'll do that. Obviously, but it would be better to do more samples per trial and more trials. Like if we can do both things, that's really better. I'm putting it in these terms of that would be better if we could do it, because a lot of the time we don't have the opportunity to capture more data, right? That's in this case we do. We just need to allocate more computation time. We can totally do that. But if you're out in the world and you're trying to get a very clarified signal of something that's happening, sometimes we don't have the luxury of capturing a larger single sample, and maybe we do multiple trials of smaller samples, and that's going to lead us in the right direction. And at some point, hopefully we can either synthesize data or find a better way to collect data, or we can use what I'll refer to later as a Bayesian approach, and update our beliefs as we go. So with that in mind, let's comment all that out, and let's think about let's just run more trials of samples and see what happens. So make that a bit bigger. I'm going to do, how about this? Let's do 500 trials of 1,000 samples. And since we know that this is a binomial process, even though it's random, even though we're randomly generating these lengths of binary, our assumption is that if we do more trials and take more samples, that we are going to lead ourselves toward a binomial distribution, toward the theoretical binomial distribution. So let's make that a small goal, although we're not going to fully achieve it here. So I'll call this binary sampling, and I'm going to put CLT on here. There's a slight implication here of what we call the central limit theorem, which I'm not going to get into aside from this sort of thing that I'm doing right now that we call the bootstrap. Bootstrap is just, let's keep sampling, right? It's sort of like that. It's a little more than that, but that's really what it comes down to. Hey, let's find a systematic way to take many more samples from the same distribution. So n bits, we're going to do 16. Number of samples, let's do 1,000. And the number of sample trials, this is just our number of trials, 500. So we're going to do 500 trials of 1,000 samples. And I'm going to just have a dictionary here. This is the final dictionary that's going to have our counts in it. So for whatever in range, this is our outer loop. This is going to be the number of sample trials, or 500 trials. I'm going to get a dictionary every time from that binary sampling dictionary. Number of bits, number of samples. And I'm just going to traverse this and pack these in to d out. So for k, v, in d.items, if that value of k is not already in d out, then we can put it there, d out sub k. And we can go d out sub k dot append. So I'm not incrementing this time. I'm going to append the values, and then I'm going to average them at the end. So I will append the value, and once that finishes running, I'm just going to traverse d out and average everything. So kv in d out dot items. We can do d out sub k is just going to get the sum of v. V is a list, right? V is a list of the different counts from the samples. So sum of v divided by the length of v. And we can return d out. And I think that function should work. So let's call this. Oh. Put that there. And I'll get that out in a dictionary. And this is going to be the counts. So this is just our, I'll snag some for loop up here. This is going to be essentially the same thing, right? So for key value in the sorted version of d.items, let's print the keys and the values. So v here is our average sample value, our averaged sample value. So let's take a look at that. And remember, this is for 1,000 samples, so we're going to see the counts relative to 1,000. And this should take a little bit to run, right? And then we have some output. So we are capturing from 0 to 16 now. So that's good. And we have, I'm going to just say, I think we have slightly better symmetry that we can see here. 7 and 9 are very close to each other. 6 and 10 are close to each other. They're not off by much from what we would expect to see in the theoretical distribution. And now we can take this and just take the same code and go ahead and look at our actual we'll look at our actual probabilities here. So this is going to be the sum of v, v divided by the sum of d dot values. And I'll round that. Should I round that? I probably should round it. Okay, I'm going to do it. So we'll round that to 4 places. Okay. And let's see. So it'll take, 5-6 seconds to run. Oh. Same error. Try that again. Okay. So then we start wondering, is this comparable to what our PMF for this would produce? Well, we don't have a PMF yet. That's what we're going to be doing next. But we could potentially ask the question, is this comparable to what our counts would produce, right? Through our sort of exhaustive counting approach. We can make that comparison. I'm just going to say that, yes, this is going to be very close. And feel free to verify that. All you need to do is call the function where we generate a dictionary based on counting, and then output this in the same way and just set them side to side. You can even traverse them and subtract the differences and see how close they get to each other. And here we could also do this. Let's say we did 1,000 trials of 100 samples, right? This is the kind of thing that you want to play around with and see what that gets you. Now, that does pretty well, and it's much faster, right? 1,000 trials of 100 samples is much faster. But notice we're missing something here. We're missing 16, okay? We're missing 16. And that's because 16 is an unlikely outcome when you just run 100 samples. And we did catch 0, but it's very likely that we wouldn't catch 0. In fact, look at the probability of getting 0 successes in 16, and look at the probability of getting 1 success in 16, right? These are essentially, that's the same exact value after rounding. So what we lose here, we really want to do more samples, and then the way we iron out our certainty, the way we trend our final distribution toward the theoretical distribution is we do more trials of the samples. So, ideally we would do a lot more, like I said, a lot more samples, like 10,000, and then, another 10,000 sample trials. But, given the constraints that we have in this case, computational constraints, I think this does pretty well. Number of samples 1,000 and number of sample trials 500. So I'm going to comment that out because that takes a while to run. And let's think about some more. I think we might be done with sampling. Let's just see. Oh, okay. So up until this point, we haven't varied our probability, right? We haven't varied the probability. We've kept p at 0.5, and it turns out that we can just work back in the Bernoulli trial with a variable p, and we can write a somewhat better function that is going to allow us to vary the value of p. So let's do that. We've got our Bernoulli trial above. I wonder if I called it the same thing. Get success? No, I didn't. Okay. Well, I'll stick with what I have in the notes. So let's do, we'll call this binomial sampling with varying probability. And this is simple enough. We can just define the Bernoulli trial. I'm going to just call it get success. And I'll set the probability at 0.5 by default. And if random, which we are importing, If random is less than the probability, then we can return 1, else we return 0. And now, when we generate n successes, or generate n bits, I think is what it's called up here, right? Generate n bits. I can just take this, and I'm going to change it to n successes, because it's slightly different from a bit now. Even though it's a 0 or 1, now it doesn't have equal probability, so I'm going to just change the name a little bit. So let's call this get success, and let's we also need to pass in a probability here. So let's do p of 0.5, and let's try this out with a probability of 0.25. So we should expect a different, just generally here, we should expect we should expect 2 1s generally, right? So let's find out. Oh, that looks like it's 0.5. What is going on? If random is less than the probability, am I calling this on 0.5? That does not seem random. Just to see, I'm trying to figure out what I'm doing wrong here. Maybe somebody sees it. Like, we shouldn't get any 1s out of this. I didn't call it internally with a value. Oh, thank you. That should clear that up. So we should never get a 1 in this case. Let me change that to 0.25. Yeah, thanks so much for that. I probably wouldn't have caught that, at least not for a couple minutes. Okay, so here we got 2 1s. We got more than 2 1s, but that's fine. 3 1s, got a bunch of 1s that time. 3 1s, 0 1s. Now, we should expect, if we were to run this with a probability of 0.25 and pack this into a dictionary, we should see a modal value around 2 if we're calling this for length 8. N trials, n equals 8. So let's see about that. This dictionary function is going to be very similar. Well, yeah, it would be very similar to what we're seeing up here. So I'm going to copy all this out, and I'm going to call this binary sampling, and let's do vary probability. Then we pass in the number of bits. I'm just going to default that to 8. We'll call it with the default. And I'll do... Oh, whoops. This is not the right function. Let me find the right function. That's what I'm looking for. Okay. So number of bits, 8. And we'll just put in a parameter here for the probability. And I'll change the name slightly. So varying the probability. And what do we need to do in here? So generate n bits. We can change this to n successes. And we pass in the number of bits and the probability. Yep. And then observed k is going to be the sum of the binary. If k is not in the dictionary, then we... Okay, that looks good to me. And go ahead and call this and see what happens. So this is going to be... I'll call it with our defaults here. And for key value in sorted items, I'll just print the key and the value. All right, let's see how that does. Oh, what am I doing wrong? All right. P of 0.5. That's why. Okay. Try that again. And we can see that this looks like it's working. And I'll say it like that. It looks like it's working. Without other functions to compare to, we don't know for sure. But I'm going to go out on a limb here and say that I think it's working. And we would expect, given that the expectation or the mean for a binomial distribution is just n times p, well, n is 8, p is 0.25, so our expectation, our modal value here, seems clearly to be 2. Okay. So we could do more here. We could do many trials of samples. I think I have that in the notes, but that's there for your edification. There's also, some simple code here to verify, right? Because sometimes you don't want to write a whole bunch of stuff. You just want to see, is this doing what I expect it to do? There's a bit of code here that does that. This is that varying p dictionary, one trial of 1,000 samples. And then I'm not going to put this, I'm going to copy and paste this into the notes, but I'm not going to walk through it. This is just 500 trials of 1,000 samples. So another function that you can definitely feel free to play around with, but because I already covered it in the last few slides, I'm going to skip it here. That's just us gaining surety or reducing uncertainty. Okay, so we've taken kind of the long way around to get to the probability mass function. And the reason I like doing that, as I explained yesterday, I want you to kind of understand what's happening with binomial, right? Like, how can we think about this in kind of a very abstracted and also rudimentary way? I think binary, counting in binary, you can't get much more like rudiment than that. And it's important to know something of binary, to know something of number systems. And so taking this approach is like, well, it's a bit of, baptism in the theory by fire in a way. That's why I do it this way. I think in a lot of cases, you would just start off with the probability mass function, the closed formula approach. So this is a fairly straightforward function. And I think we've got some basis for understanding why this function works the way it does. So we can see this in multiple parts, and we'll think about it in multiple parts. Notice that we have combinations in here. Why do we have combinations? Why is that in there, right? This is one of those things that you see this and you're like, well, there's a reason for this. And that roots us back into counting. And that's part of the idea here. Well, if we are looking at all the different ways that you can get, sum up to 3 in 8-bit binary, then that looks like a combinations problem. And so you see combinations directly in here. In this case, in the case of the binomial PMF, we take the probability and exponentiate it to the number of successes we're looking for the probability of. And because we're balancing binary, we're balancing successes and failures, we also want to look at something like the complement of that, right? The complement of the probability raised to the complement of the number of successes. So we're if you get into it, if you feel like it, look up log odds. There's a very similar idea to that. We see this construct in probability theory all the time, where you take the probability of something and you multiply it by the complement of the probability. So that's something that we do pretty constantly. I'm going to, So the 3 parameters of this, the number of Bernoulli trials, n, which we've been talking about, that's been our number of bits. P, the probability of success per Bernoulli trial. that stays constant across our trials. And k is the number of successes for which we want to find the probability. So other parameters of this, as I've been saying this, the expectation, right? What do we expect to get out of a specific binomial distribution? Well, the mean of that is our expectation, and that's just the number of trials multiplied by the probability. And then variance is a fairly simple formula as well. This is just the number of trials multiplied by the probability multiplied by 1 minus the probability. So you can see again here, we've got that p multiplied by 1 minus p construct that's going to pop up quite a bit. Of course, if you want to take the standard deviation of this, you would just square root this formula. So when you see this written, x is distributed is a random variable that follows a binomial distribution with n trials and probability per trial p. So we could do this with other distributions as well, and I just want to say this because when you see this, I don't want you to be afraid of it, right? I want you to see it and read it as it is. Like we could say y, if I do this, y and normal, and then let's do mu and standard deviation. I would read this as y is a random variable that follows a normal distribution with mean mu and standard deviation sigma. So we could do this for any number of things, right? Z follows a Poisson. And for Poisson, we're going to have a lambda. And that's it, actually. So Z is a random variable that follows a Poisson distribution. So that's just a little bit of notation. You're likely to come across this as you study up. So I just want to touch on that very briefly here. Okay, so now we're going to get into coding the binomial PMF. You're going to code two functions, and you're going to code these in 4 minutes, factorial and combinations. Here is the formula for combinations, right? N factorial over n minus k factorial multiplied by k factorial. So code factorial, code combinations, and yeah, try to do that within 4 minutes. I'll set a timer now. All right, I see some good solutions in there. Here, let's do this. I'll just say using PMF right there. Saw somebody do the optimized solution, or the somewhat more optimized solution. That's awesome. Okay, so def factorial of n. I'll just put that up a little bit. The product we initialize to 1, and then we just say for num in range, and we go from 1 to n plus 1. We could start at 2. Computationally, it doesn't matter really, but it would be minimally more optimal. So return the product, and I'm going to write not the optimal version here, but or more optimal version. I'm just going to write the normal flat one, that is the factorial of n divided by the factorial of n minus k multiplied by the factorial of k. Okay. So those are the components we'll need for the binomial distribution, for the binomial PMF. And we'll skip this one, the why do you think combinations is part of the binomial PMF. I think I already sort of gave that away. And we'll get right to this. So 3 minutes, code the binomial PMF. N is the number of Bernoulli trials, P is the probability of success for any given Bernoulli trial, and K is the specific number of successes for which to find the probability. I'll make this formula just a little bit bigger. And yeah, go ahead and get started. Okay, so let's code this. Put that up there. And this is just translation of this directly into code, right? So I'll call this binomial PMF, and n, k, and I'm defaulting p to 0.5. And we can return combinations, right? That first part, combinations, and choose k. And then that second part is just p to the k, right? So p to the k. And then the third part is 1 minus p. And that is to the n minus k. So that looks right to me. And now that we have this PMF, we can start easily answering, kind of textbook questions. So let's see what we can start answering here. So here are two problems. Maybe I'll shrink this back a little bit. Oh, it's 3 problems, actually. Those are a little small. Maybe I can make that a little bit bigger. Oh yeah, let me know if that's not readable, and I can try to make them a little bit bigger. But if that works, give me a quick thumbs up in the, not in the chat, but in the, just in the visual. Is that readable? Is that all right? Yeah, okay. So we'll take 4 minutes and just answer each of these. What is the probability in 12 coin flips of fair coin that you get 7 heads? And then we have just a couple more here. And then this is kind of like classic textbook problem, right? And we want to make sure that you know how to answer these kinds of textbook problems. So go for it. Let me know if you need these to be larger at all. So I think everybody's pretty much got the hang of this. Probability in 12 coin flips of a fair coin, getting 7 heads. Well, we're assuming a probability of 0.5, right? And K is going to be 7. That's 7 successes out of 12 trials. And we can just call this with the binomial PMF, and we should get the right answer. I think there's pretty strong consensus on a lot of these. So 0.1933 or 0.1934. We could round this. I would round it to 3 or 4 places. Okay, so this next one, sitting on a park bench, there's a probability of 0.3 that any goose walking by has black feet. So let's set that to 0.3. The probability that 4 out of the next 12. So that's 4 out of 12. And again, we can just call the binomial PMF there. And it looks like that was 0.2311. And then at the cat cafe, there's a 40% chance that a cat is a Siberian. What is the probability that 6 out of the 14 cats at the park, sure, cafes, parks, cats, dogs, either way. N is going to be 14 here. And we're talking 6 of them, and there's a 40% chance. So it's just like that. So, if you can pick apart the question effectively for binomial, it's really easy. You just need to know the number of trials, the probability, and the value that you're searching for, right? So that's pretty straightforward. As we learn a couple more of the distributions, you're going to see also that sometimes it's about figuring out what distribution you're working with, and also the question of, is it a probability mass function problem, or is it a cumulative density function? Speaking of which, we're just going to get into that right now. That's exactly what we're going to do. Okay, so here we've got a CDF function for the binomial distribution. Okay, this is the corresponding function to the binomial PMF. And this might look, if you're not very familiar with mathematical formulation, this might look a little bit daunting at first. But I want you to notice that inside of this is the binomial PMF, and this I, this I is really just representative of values of K, right? So what we're doing here is we are summing. This is just summation up here. This is the summation symbol. And we're going to accumulate all of the results of this whole thing. That's all it is, right? So this is a simple accumulator pattern when you think about it that way, right? So we're going to set K to 0 and, plug in N, K, and P, get the result from our PMF. And then we're going to set K to 1 and do it again, and to 2 and to 3 and to 4, up until our desired value less than or equal to K. So I think this should be pretty straightforward. If there are any questions about what we're doing there, definitely ask now. We can come back to it as well. But notice that if we're trying to consider the probability that x is less than or equal to 4, we can also sum this outright, right? We can say, well, that's the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 plus, right? It's just that. It's just, we can use a for loop. We can also call the PMF 5 times in this instance. And either of those things should get us to the same answer. So I'm going to have you code the binomial PMF, and you're going to find your prior function to be helpful. And why don't I paste that in to the Slack. I'll paste that into the Slack in just a moment in case you don't have it. I'm going to set this timer to 4 minutes and go ahead and get started on this. All right, I'm going to go through a quick solution of this, and then we'll take a break. Let me go ahead and shrink this down. Okay, so I'm just going to do that. And this is a simple accumulator pattern, right? So we can say, I'll just define it really fast. I'll do n and then k high. Is that how I did that? Oh, I think I did np then k high. Okay. np k high. Although I do like setting the probability to 0.5 by default, but I'll do what I did on the slide. Okay, so simple accumulator, right? Cumulative is in the name of this cumulative density function. So just want to drive that point home. So for k in range, and we're going from 0, I don't need to put 0 explicitly here. I can just do k high plus 1. We want to be inclusive of that high value. And then cumulative is going to be incremented by the binomial PMF, n, k, and p. So we can return cumulative, and yeah, and that should do what we expected to do. You know what? I'm going to fix it on the slide instead. I'm just going to do this because I want to follow that same pattern, right? Binomial PMF, NKP. So I'm just going to switch this around. So be careful of that when you call this function later. Okay, let's take 6 minutes, and I'll see y'all back here shortly. Okay, so let's pick up from there. I should probably test this. Why don't I do that really fast? Let's do n of, let's do 8, k high of, let's do 2, and a probability of 0.5, and just see what that looks like. 0.1445325. That seems very reasonable. If I change this to 0.25, then that seems, that definitely seems like it's working. Or more definitely seems like it's working. I feel pretty confident about that. Okay, so let's apply this to kind of just a basic textbook problem. You're going to solve this CDF problem. There are 8 components in parallel and functioning independent of each other. So this is in some kind of circuit. At least 3 of those components need to be operational for this given circuit to function. The probability of any given component being operational upon observation is 0.7. Okay, so if we're thinking about what this looks like, right, we've got these components, right, and there's 8 of them, and they're all in parallel to each other, meaning that if this component goes out, for our purposes, it just means that if one component goes out, the other ones are still functioning. Let's just think about it that way. And so these are independent of each other, and each of them has a 0.7 probability of being operational upon observation, right? So we're imagining maybe they're flipping in and out of being operational. So what is the probability that at least 3 components are operational upon observation? So I'm going to put 3 minutes on the timer. And yeah, see where you get on this. Okay, so let's walk through how to solve this. Or if you want a couple more minutes on this, give me a quick thumbs up. If not, I'll go ahead and take us through a solution. Okay, I'm going to go ahead and do this. I'll copy this and put this in our document. Okay, so 8 components in parallel. This is our n as 8. At least 3 of those components need to be operational for a given circuit to function. Okay, so I'm gonna just put k high here, but notice that we're saying at least 3, right? So I'll come back to that in a second. Our probability of a component being functioning is 0.7. So let's think about this. If we're going to call the binomial CDF and print, and we're putting in a value for p. We've got n here. It's really this k high that we want to think about. Now, if I'm approaching this as 8 things in parallel, and we need at least 3 of them, right? So there's 8, and we need at least 3 of these functioning. Now, we can think about this in a couple different ways. If we're going to look at these, and it's 0.7 probability that it is operational, then instead of, since the CDF is going to get us less than a certain amount, we can just do 1 minus the probability of this, right? This is one of those things that we do with the CDF all the time. We get the probability of the complement. So I'm going to set k high to 2 because we're thinking about those 2, right? We're thinking about at most we can have 2 be failing, right? So if we do this and then just subtract the binomial CDF from 1, then we should be in a good spot. Okay, let's run that, and I saw a couple people had answers around 0.98. That seems, yeah, that looks correct to me. So that's pretty good. And this is one of those types of textbook problems where they say, oh, we've got a bunch of components in parallel, and what is the probability that at least this many of them are working? The kind of answer that you're going to make for that is going to be 1 minus a CDF. That's a pretty common type of question. Now, there are other kinds of questions that that you might get. Things like, well, how many components do you, or how do I say this? How many components do you need to have functional in order to have 99.5% certainty that the circuit is operating when you observe it, right? That's another kind of question, and we'll maybe do some questions like that on our technical interview day, like our review for the technical interview day. But I'm going to leave you to think about that for now, right? Like the kind of question that is, how many of these components do you need to have be functioning? How many components do you need to have functioning in order to achieve this level of operation? Or what should your fail rate be for your component if you have this many components and this many functioning? What should your fail rate be, right? So you can imagine varying your n and your k high and your p here in order to achieve some specific goal some specific goal for your probability of the circuit functioning correctly. I think oh, okay, yep. So our next function, and let's put 4 minutes. Let's put 5 minutes for this one. You're going to code a PMF dictionary function, and this is going to look a lot like the prior functions that we've coded, honestly. So let's do 5 minutes for that. You should have 4 parameters, the number of trials, right? So n, k, and p, right? But here we're going to do a k low to k high, inclusive of both. So you only want to include in your dictionary from some number of successes up to some other number of successes, right? So if you have 20 trials, but k low is 5 and k high is 15, you only want to represent the probabilities for 5, 6, 7, 8, 9, 10, up through 15. Okay, so let's put 5 minutes on the clock for that, and yeah, and then we'll go through a solution. Let me know if you want a couple more minutes on this with a thumbs up in the Slack. I'll give you like 20 seconds on that. All right, let's code a quick solution. So this is pretty straightforward, I think. It looks a lot like a lot of the things we've already done. I'm going to do binomial PMF dictionary and n, k low, k high, and then a probability of 0.5 by default. And I'll set my collector here, this dictionary, and I'll say for k in range k low to k high plus 1, d sub k is going to get, it's just going to get that binomial PMF, right? Binomial PMF nkp, and we'll return the dictionary. So when I call this, let's set n to let's set it to 30, and let's set k to 10, 10 up until 20, and we'll do 0.25. So for k, v, in d.items, we can see what this distribution looks like, right? So print an f string, oh my gosh, there we go. All right. So this looks pretty reasonable. There's something kind of interesting about the binomial distribution that we're going to actually get into with the Poisson distribution. As we increase the number of trials and we lower the probability of success per trial, we're actually going to be approaching a Poisson distribution, as we'll see shortly. But notice, once we get out to 20 here, even we're not very probable even around our expectation, right? If I lower this somewhat, if I brought this down to 7, we'd be able to see that. But it's just something to keep in mind as you grow the number of trials and reduce your probability. You're going to be having even your expectation have a very low probability of success. I think that's kind of an interesting facet of binomial. So there's one more slide on here, and this is really just considering the binomial CDF dictionary. And I think this will, I'm just going to copy and paste this in, and we can look at the output of it. Notice the only difference between this and the prior function is that I'm collecting from the CDF instead of collecting from the PMF. And maybe this is obvious, but I just want to point it out. The probability that we're going to get, if we have 8 trials, the probability that we're going to have 8 or less successes in 8 trials is going to be 1. And so with binomial, we're always going to have a cumulative, the cumulative probability across all trials is going to be 1. That is going to be a different thing that we'll see with Poisson, which we're going to start looking at right now. So I'm going to switch documents to this Poisson.py. So if you're following along with the code on GitHub at all, just switch over to Poisson.py. And I'm going to get over here and we'll start looking at this. We're not going to get very far with this. Well, we'll take a chunk out of it, I think. I think we'll be able to establish the rationale for Poisson, at least. And then we'll save the Poisson PMF probably for Saturday. Okay. So we're going to think about the idea of a Poisson phenomenon. And then we're going to consider the Poisson PMF and the relationship between Poisson and binomial. So why don't we just like generally define the Poisson distribution? So when we're thinking about something that that follows a Poisson distribution, we often think about it as events over some span of time. And it doesn't have to be time, but we'll start with this idea of time and kind of expand from there. So there are some constraints to what these events can be. So any event, any success, right, is a quantifiable event, and any event that occurs has to be independent from another event. So here's a way to think about this, just something to tie this to in the real world. If you are working at a store and, on average you see 5 people come in the store every 10 minutes or so, that's your average, right? You can move that window of 5 minutes anywhere, and you would still expect to see 5 people come through. And by that, I mean that there's a consistent rate, a constant. Well, let's say this says constant, but I actually think that should say consistent, and I'm going to change that because the rate is consistent over a long period of time. It's not constant, as in it's always going to be 5 people every 5 minutes or 5 people every 10 minutes. That's just not how the universe works. So I'm going to just say this is consistent, not constant. When we're thinking about this, we're going to assume that 2 people who enter the store are going to be independent of each other, and also one person entering the store is going to be independent of themselves at a different time, right? So that's not really like the real world. We usually, don't randomly go in and out of stores or something like that. We'll probably go to a store based on the last time we went to a store. There's some, distribution of some way to quantify the, there's some random variable that probably represents the time between the last time we go to a store and the time that we go to a store next, the same store. So that's, in Poisson, we're going to assume that any event is independent of any other event, and those events are are identically distributed across all these spans of time. We'll deal with time, all the spans of time that we have in consideration. We're also going. This is a lesser. This one is of lesser importance. This 2 events cannot occur at the exact same instant, and I'm going to try to give a sense of why we don't need to really think about that too hard. But let's draw this a little bit, because I think the idea of Poisson is fairly intuitive. So let's say we have a span of time, and let's just deal with 4 minutes. In 4 minutes, let's say we assume that 10 events happen, right? So in 4 minutes, we have an average, or a lambda, of 10 events. Those 10 events can happen anywhere in this 4 minutes, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? They could happen like that. That's fine. That's totally reasonable. They could also happen as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They could happen like that. That is also totally reasonable. We have to keep in mind that these events are independent of each other. These are not related, or we need to assume that they're not in order to apply the Poisson PMF. But we're going to assume that in 4 minutes we would expect 10 events. Does that mean we are going to get 10 events in 4 minutes? No, it doesn't mean that. It means that that's what we would expect. And there's all these different ways we can arrange 10 over this time of 4. Notice that 4 minutes here is not discretized, right? This is not discrete. This is continuous. If we this is sort of why 2 events occurring at the same time is okay. It's a stipulation, but it's there for theoretical reasons. The reality is, if we have precise enough instruments, because there is an assumption that time is continuous and not discrete. At least that's the current assumption. You can have 2 events basically on top of each other, but if we have fine enough instruments, we're going to see that they do not occur at the exact same time, because we're assuming that is not possible. Okay, so if we know that there are 10 events that can occur in 4 minutes, we have another way of thinking about Poisson. We can have another timeline where we represent 8 minutes. And in 8 minutes, if we're assuming these constraints, right, the constraint that the rate of arrivals, the rate of events is consistent, that the successes are independent and discrete, they're also discrete, and random, and that they can't occur at the same instance, then in 8 minutes, we would expect, our expectation would be 20 events, right? So we've got a lambda for 4 minutes. So this is our 4-minute lambda. An 8-minute lambda would be, well, it's just double, right? It's just double 4. So that's just 10 times 2. So that would be, we would expect 20 events. Now, this may feel a little hand-wavy, and well, that's fair. There's a lot of I guess, constraint and stipulation that we put on this, but this is actually a really powerful way to think about things. We can just have a lambda, and knowing lambda for some phenomenon, we can ask the kind of question, given an expectation, given a lambda of 10 in x time, right? What is the probability of 20 events in let's call it x times 2 time. It's kind of amazing. There's very few parameters in there, right? It's just our expectation. We're not talking about, we're not talking about a probability exactly. Well, there's an implicit probability, actually, but we'll get to that in a little bit. We're not talking about an explicit probability, and we're not talking about a number of trials. We're simply talking about our expectations around a given span of time or a given volume. And we can, carry this out a little further. If we were thinking about this in terms of binomial, we might say there's 1 minute. Let's say 1 minute. In 1 minute, we expect 1 event. And if we're thinking about this in a binomial way, then we might divide this like this, and say that there's a probability of 0.5, and there are 2 trials, right? And our expectation is that one of these is going to be a success, right? It's either one or the other, or maybe it's both. So what happens if we, instead of saying, there's only 2 trials here, what if we say, oh no, there's actually 4 trials. How does that affect our probability, right? So if we do this over and over again, and we think about this in terms of Bernoulli trials, and we do this and we trend n toward infinity, well, that's going to reduce our probability, right? Our probability is going to trend toward 0 as we do this. So we're discretizing time, we're discretizing the space, but we're going to discretize it to the point of it being continuous, right? So we do that, and we have the emergence of Euler's number as a decay factor for the probability. And that's kind of amazing. We get a nice little like closed formula for the PMF. And I talk about that. I actually, if you want, there's a link to a playlist of videos. I think it's like it's probably 4 videos describing the emergence of Euler's number. So, oh gosh, I can't just copy that, can I? Well, that's great. Okay, well, I'll paste it in a minute. Let's just go straight to the Poisson PMF and break this down. So, oh, thanks. Yeah, awesome. So that's partially why we have this emergence of E. You know, E is in there as somewhat of a decay factor. I think of it that way. You know, somebody would probably be up in arms hearing me call it that. So we have lambda, where lambda is our average number of events, the number of events we might expect, something like that. And K, we're trying to find the probability of K events occurring. So, you know, given that we understand that 5 people come into our store every 10 minutes on average, what is the probability that 2 people will come through in 5 minutes, right? And amazingly, we can just say, well, that's e to the negative 5 multiplied by 5 squared over 2 factorial. And that's going to give us a theoretical probability for that happening. I think that's pretty cool. It's one of those really weird emergent things, and yeah, I think it's pretty neat. So I'm going to let's just look at a couple of problems that look like this. On average, 10 people visit an ATM in an hour. What is the probability that 12 people visit the ATM in an hour? Well, our lambda is 10, right? That's what we expect. If our lambda is 10, we expect 10 people, or our average, right, is 10. And we're looking for the probability that 12 people will show up to that ATM. So we can just plug these numbers in, essentially. So that's just e to the negative 10 multiplied by 10 to the 12 over 12 factorial. And the probability of 12 people visiting an ATM during that 5 minutes of time is 0.0948. So here's another one. A specific space telescope takes random images of deep space. On average, 23 supergiant stars are seen in an image. What is the probability that 2 randomly selected images will have a total of 35 supergiant stars in them? Okay, so here we're given this average, 23, but that 23 is relative, right? That 23 is relative to to one image, right? So one image should have on average should have 23 stars. So 2 images on average should just have 46 stars. And so we change our lambda from 23 to 46. And then we're looking for the probability that 35 stars are across those 2 images, like the sum total of stars will be across those 2 images. And we can just plug those numbers in again. So e to the negative 46 multiplied by 46 to the 35th over 35 factorial. And what we see there is about 1.6% probability. Cool. So I'm going to have you code, let's see, do we have time? Yeah, we have time. I'm going to have you code the Poisson PMF really quick. This should, you can just import factorial if you want, but feel free to write it. And you can either hard code E, which I'll put in the value for E in just a second, or you can import it from math as well. So you could do from math import E, comma factorial. You can hard code factorial. You can hard code E. But all of that's there. So I'm going to put 4 minutes on the timer. And go for it. Okay, so I'm just going to code this really quick. Okay. And I'll just import factorial and E. So from math, import factorial and E. And I'll just define our Poisson PMF as such. So lambda k. Notice I'm not calling this LAMBDA. That's actually a reserved word, as you can see. So a lot of people will call this lam. That's totally fine. I usually just do lambda like that. And we can return lambda to the k multiplied by e to the negative lambda. Sorry, I'm doing this in a different order. Oh. E to the negative lambda times lambda to the k and divided by factorial of k. So let me just test this really quick. A value I know offhand is lambda of 10 and k of 10 should be something like 0.125. So let's try it with those. Only accepts integral values. What am I doing wrong? Lambda e to the negative lambda times lambda to the k divided by... Line 5. Whoa. Oh, that's why. 0.125 and 0.125. Sorry. 10 and 10. This should get us a probability of 0.125. There it is, 0.125. Okay. All right, so let's call it there. In the next class, I'm gonna, continue tying binomial into Poisson just a little bit, but then we're going to, do a lot of the same thing that we've been doing. I'm not going to have a sampling or a counting approach for Poisson. We could do something like that. Instead, I'm just going to maybe write some code to justify the statement I made before that the binomial distribution tends toward the Poisson distribution as we increase n and decrease p, and hold lambda constant, right? We don't want to increase the expected number of events for a specific span of time. But I want to justify that a little bit with some code. I think it's always good to, sort of use code to prove to yourself that something is the way that people say it is. So I've got some code to do that. Otherwise, yeah, feel free to sign off. Have a great Friday, and I'll see you all on Saturday. I'll stay on for a few minutes to answer any questions, and yeah, have a great night.